Welcome to this session. In last couple of sessions, we have learned how to create geometry, different approaches, different options, and things like that. And hope everything is clear with you. And now I am going to start with next thing into this, and we will start with our approach with the 3D, a couple of examples, and try to understand many things into that. Now, coming to the when I say 3D structural analysis, it typically involves model 3D geometry and element required for it. So, if you recall my initial session on introduction to FEA, I talked about there are three different type of elements in general, four type of elements in general: 1D, 2D, and 3D, and 0D. So 1D is used where we can represent geometry by line, and 2D is used where geometry can be represented by planes or surfaces, and 3D elements are used where the geometry is in the solid form, that is a 3D. So, keeping this in mind, I'm going to coming directly to the 3D, and I will go backward like 3D, 2D, and 1D, and then 0D. So let us start with our 3D. Let me share Ansys help. Okay, and you can go to the Ansys help. So slowly we will try to get acquainted with the Ansys help. So this is the help which we will typically use when we are working with the Ansys Classic. Okay, so this help combines together based on this will have everything together based on the installations you have done. It may have Ansys Workbench or Ansys CFX, Design Modeler, or Turbo System, or anything. I mean, Autodyne or whatever. Okay. So these anyway we are not going to see. This is also we are not going to see. This is Ansys CFX. This is a Design Modeler. Then this is a FE Modeler, and this is a mechanical. Okay. So part of structural analysis and it's a workbench kind of simulation, and we have a turbo system, a remote solver, RSM, and meshing, and various things. Now I am mainly focusing, as we are learning Ansys Classic, we will focus on this. And here again you will see various user guides are there, like LS9 user guide, APDL information, advanced techniques, and things like that. And into this you will also see there is something called then there is a meshing guide. So there is the element reference guide. Go to the element reference, element classification. Click on this. You will see the list of. You will see the table which lists all the elements used by Ansys Classic. Whether it is a structural analysis, whether it is thermal analysis, whether it is electromagnetic analysis, whether it is electric analysis, or whatever. So you can see structural elements are listed here, thermal elements are listed there, fluid elements are listed, electric elements are listed, coupled field elements are listed, contact elements are listed, and various miscellaneous elements are listed. So our now focus will be mainly on solid elements. So we said solid elements we will be studying, and one of that element we already studied, that is a solid 187, couple of solutions or couple of analysis, whatever we have done during till this time, that is a piston example or the beam example or bracket example and so and so. So we have used blindly this something called solid 187. So when you click on any of the element, it pops up the information of information regarding it gives you the detailed information of that element, and you can just go back and check the when I click on this solid 187 is a 3D element with 10 nodes. So it has a 10 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and is a tetrahedral structural element. Is a tetrahedral element. Shape is a tetrahedra. So you can see the solid 187 is a higher order 3D 10 node element, and solid 187 has a quadratic displacement behavior. I will explain this terminology later. Let's try to just understand what was that we have used. Okay, so it gives you the detailed information of how many nodes this element has, or what is the behavior of this element. The element is defined by 10 nodes having 3 degrees of freedom at each node. Each node is subjected to the nodal X, nodal Y, nodal Z translation degrees of freedom, and the element has a plasticity, hyperelasticity, creep, stress, and so many other characteristics or capabilities it has. And this element requires whatever the input data required, it is summarized here, and then it also gives you the information what output you can get from this. So you can get the stress output, strain output, you can get the nodal results, elemental results, and so and so. So this all information is very, very important to understand, and you need to grasp it slowly. Whenever you use some element, go to this guide, click on this element graph, go to this table. Once you go to this table and try to understand the element by clicking on particular element. So we have used blindly this element. I said don't ask the question. That time I said I will explain it. I have briefly given the idea. Now we will try to understand what exactly is this 3D element, what are the different shapes, how we can obtain it, different kind of shapes, which are these elements, what is the difference between these various elements and all that. I will explain it. Okay. So coming back to our shapes of the element, there are three standard shapes of the 3D elements. One is called brick element. Other is called one is called brick element. So brick element will look like this. Okay, and this element has node at each location. The node at each location. It typically can have minimum it requires 1, 2, 3, 4, 5, 6, 7, and one more node will be here, 8, which is hidden. So I'll just draw a kind of faint line so that you can understand it. Okay, so this is a big element with 8 nodes. So it can have the more nodes. It can have the more nodes, but I am not bringing that scenario now into the picture. So another element is tetra element. Okay, we have tetra element like this. Tetra set, which obviously will have minimum required nodes will be 1, 2, 3, and 4, and then find another element which you can come across. It's not so popular, but penta element. But you may come across this element. Okay, penta element might be something like this. Okay, so it may require minimum 6 nodes, 1, 2, 3, 4, 5, and 6. Okay, and then there may be more nodes. I am not talking about that. Okay, then there may be more nodes. I am not talking about that. And these are the basic sets of the element. These are the basic set of the element. So there will be some mid-side nodes. There will be some mid-side nodes to each element. It may have one mid-side, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and basically 8. So Greek element can have either 8 or 20 nodes. Okay, and then ket element can have 4 or 10 nodes. We already seen the 10 node element, solid 187. So 1, 2, 3, 4, 5, 6, and 4, 10. Our penta can be 6 or 9, 15 nodes. Okay, so you can have something like okay. So the element can be brick, penta, or tetra, or sometimes this is also known as hex element. Okay, sometimes this is also known as hex element. Okay, so or this is also known as the wedge elements. Okay, So different names can be given by different people, but basically shapes remain same, hex, tet or penta. Okay, so these are the commonly used shapes available. These are the commonly shapes available in a 3D. So now let's go back to our help and try to see the different elements. What are those? Okay, solid elements. So solid 45, now you know, it's a 8-node brick element, isn't it? Brick kind of shape, but this can also take a penta shape or tetra shape based on the situation or the geometry complexity. Now, then solid 85 is again a brick element with 8 nodes. You can see, again it can take a penta or tet shape. So you can see the solid 45, which is a 8-node element, isn't it? It can take tetra or penta shape. Then you have a solid 65, again it is an 8-node, and it can take penta or tetra shape. And then you have solid 92, which is a 10-node tetra element, isn't it? 10-node tetra element, similar to solid 187. And then you have solid 95, which is, now you can see, 20-node brick element, or this can also take a 15-node prism shape, or this can also take 10-node pyramid or tet shape. And then you have a solid 147, which is purely a 20-node element, isn't it? But it is a P element. You can see something more is appearing here. We'll learn more about this P element later on. And then solid 185 is again a brick element with the 8 node. Brick element with the 8 node. And solid 186 is again 20-node brick element. You are coming across many different, and solid 187 is again 10-node brick element. Solid 285 is a tetra element with 4-node. Okay, so different elements are there. We'll try to use many of these elements, try to solve some of the examples. We'll try to understand what is difference between each and every element and where to use what element. Okay, so this thing we'll see, at least now by now we are very much clear. There are 3 shapes: tetra, penta and brick. Either it can be a 4-node, or it can be it can be 8 or 20-node brick, or it can be a 4 or 10-node tet, or it can be a 6 or 15-node penta. So now let us start our discussion with something interesting. Let us take some example. Okay, let us take some example and try to understand how we can obtain this shape of elements in our meshing, because element and nodes is the result of meshing. We'll try to create a simple geometry and try to understand, try to obtain different shapes. Now, with whatever the knowledge we have, with that we have understood that solid 45 element can take a tetra or a prism or brick shape. So we'll try to get these different shapes in one model using different options. Let's first get brick shape and then try to get a tetra shape, okay, and then try to get a penta shape. Now we'll take a simple example of again a cantilever beam. We have solved this problem. Okay, assume that this is a cantilever beam with rectangular cross section. This is 100, this is 200, okay, and this is 1,000, and this is 1,000 Newton, and we have let us say material steel. Okay, now we will try to solve this problem and try to understand these element types, element concepts, different sets of the elements in a 3D. We will solve this. So now before I solve any problem, as I said, what you have to do is you have to create something called, you should remember these 4 stages. Now you might wonder why I am saying 4 stages. Don't forget the pre-planning stage. So 0th stage is a pre-planning, first stage is a pre-processing, then second is a solution, and third is a post-processing. Now our problem should start with the pre-planning. Now we are trying to understand 3D elements, so the geometry should be created in a solid form. So I will create a box or a block of 1000 by 100 by 200, and then I will use a solid element, 3D solid element, and then mesh it. Steel material properties I will convert into the Newton per mm square and try to use that Young's modulus like 2 to the power 5 Newton per mm square and Poisson's ratio 0.28 or something like that. So this gives a this completes our pre-planning stage. Once we are complete with the pre-planning stage, you can jot down all these things into the paper, onto a paper, and then keep it ready for the ready reference when you actually start with the Ansys. Now I am starting with the Ansys. Now I am starting with the Ansys. Again, we are doing the structural analysis, preference, the structural, and then this is a H method. We'll talk about H and T method difference. Okay, click OK. Preference, element type, add. Then we said a solid element. You can see it starts with like quad 4 node. We are not studied 4 node element. Quad type of element we are not studied, but we have studied a brick element. That's what we said, brick 8 node 45 element. Below, from this below onwards, all is the list of what you see in the help, whatever I have shown in the help for 3D elements. All these are the 3D elements. Solid 45, solid 185, solid 186, solid 95, solid 46, solid 191, solid 65, solid 285, solid 187, solid 92, solid 272, solid 273. These are the different type of elements. Now I am taking this solid 45. Above this, whatever the list you see is a 2D element, 2D plane elements. That we will see sometime later when we discuss the 2D elements. Now we are discussing 3D elements or solid elements. Now I am selecting a brick node, or any element below this will work. Any element above this may not work with the volumes. Okay, so I am selecting solid 45, click OK. So you can see the name is appearing solid 45. For this element, then once the element is added, close it. Then no real constant is required, and then material properties. This why real constant is not required, I will explain it later on when I discuss 2D elements. Then material properties, we are going to define structural, linear, elastic, and isotropic. Now I say 2 to the power 5 and 0.28 the material properties. Click OK. Exit. Now no sections are required. Then modeling, we said we will create a block using any of the option. Now any option is valid for you. Okay. So input these values appropriately. This is the length, this is the height, this is the width. Okay. Just change the view isometric and then your model is ready. If something more to be done, we'll do it. But now modeling is done. This is only a simple problem we are solving again. Similar problem we have solved last session, but we are trying to discuss we are trying to understand the different aspects of the 3D element. That's why we are again repeating this example. The meshing. Now in the meshing, we have to generally before meshing in a meshing there are two options. We'll use now, let us say, mesh tool approach. There is automatic meshing and manual meshing. I'm discussing now again automatic meshing. Okay. So mesh tool, click on the mesh tool. Once you click on the mesh tool, you can see various options are there. And here you can see the hex or take option comes. Okay. By default, it is a take. And when you click on this mesh button, select on this, click OK. So you can see tetrahedral elements are generated. And we said that the solid 45 can take a tetraset. That is why you could do this meshing successfully. Now I don't want to do this tetrahedral element. I want to generate let us say hex element or brick element. Click on the hex here and then click on the mesh. You can see that brick shape of the element is appearing here, isn't it? So brick is possible. Now penta, I will discuss it later. So brick will have 8 nodes, or tape element, whatever you have seen, will have the 4 nodes. So either you can generate 4-node tetrahedral element, or you can generate using a mesh tool. Okay, and this is what something called, when I am on the tape, you can see the toggle is here at the free. When I am clicking on the hex, it is switching to the map. Okay, so it means there are types of meshing, that is a free meshing, map meshing, or there is another classification of meshing on the basis of how you are creating manual meshing or automatic meshing. Okay, now whatever we are doing this is a automatic meshing, not manually. I mean, it is doing automatically. It is deciding what is the number of element, what is the edge length, element edge length, or number of elements to be created. User is not controlling here, or I am not controlling here how it should be, either whether it is a tape or hex. Okay, so that is, or I can control this to some extent. Then there is something called fine meshing and coarse meshing. There are a lot of terminologies coming up. We'll discuss one by one. So when I click on the coarse meshing, I may get a different mesh. When I click on the fine meshing, I may get a different meshing. Okay, and when I click on tet fine mesh, I may get different meshing. So there are various. You can see the fine meshing is appearing something like this, whereas the coarse meshing is appearing something like this. Okay, so you can see the size change, variation change into the elements. This will typically happen based on. So there are few things we are noted down. There are things we are noting down. There is something called fine mesh and coarse mesh. Then there is something called manual mesh, automatic mesh, and manual mesh. Then there is something called free and map mesh. Okay, so these three things we'll discuss sometime later. Okay, now let us solve the problem with one of the option. Let us say mesh tool, find course mesh, take mesh and solving it. Okay, this is the mesh I want to use and try to solve the problem. Then next step is, these are the few steps we are not using. Okay, now here we will discuss that also later on. Then there is something called, I will note one more terminology, that is something called quality of the elements. Okay, quality of elements. So these are some of the things we will discuss is later on. But as of now, I want to discuss this. Let me complete this problem and then we can switch over to those concepts. So I am using this, that can be done in the checking controls and numbering controls. Okay. Now loads, go to the loads analysis type, new analysis, static, define loads, apply structural displacement on areas, select this area, click OK. Okay, and then apply structural force on key points, these two key points. I'm dividing the load. Okay, minus 1000 divided by 2 number of nodes. Okay, then solve. Click OK. General post processing, plot results, define set. You can see 0.00, and now we can capture this image for further processing. Okay, I am capturing and saving this image for okay, and control plot, element solution, stress, 1 versus stress, and I want to save this also. So as plot control, capture this image. Okay, so this is done. Now let us go back to the pre-processing. We have seen the results, what is stress 0.7 and deformation also we have noted down. You can easily calculate this using the analytical approach, bending theory, and try to verify the result. Now I want to change this mesh to the hex mesh, meshing, mesh tool, then change it to the hex mesh, click OK. Yes, I have obtained some hex mesh. I am not required to apply the loads and boundary conditions again. I can now directly solve this once again. Okay, I solve it. And now once again I go to the general post processing, plot result, deform shape, and I can see the deformation plot. That is a 0.0255. And whereas I have seen the deformation, we have seen the deformation 0.0085. There is a difference. There is a difference in this result and that result. And element solution, 1 versus stress is a 1.496, whereas the result which we have seen has a 0.72 Newton per mm square. So there is a difference in the result, isn't it? There is a difference in the result. The results are really not matching at all. So there is a huge question now, which element, what went wrong? What are the problems? So there are a lot of questions now, isn't it? There are a lot of questions I can see. So let us now try to note down a few more things, like why there is a difference in the results. And another question I am noting down is, there is which result is correct, which one is correct. Okay, so meantime what I expect is, what you can do, you go through this problem, you can work on this problem and then get the analytical solution using game theory and keep the answers ready. I will also come up with the analytical answers and we will try to verify which results are matching, and then we will continue our discussion which one is correct and how to improve the results of incorrect way, whatever the incorrect way we have got, and we will try to bridge this gap with this understanding. I have noted down some of the action items for the next. So some of these points which we will discuss next time is, what is this fine meshing? Okay, what is the fine and coarse meshing, automatic mesh and manual mesh, pre and not mesh, quality of element. First I will take these two questions, why there is a difference in the results and which results are correct. Okay, so with this I am stopping here. With this I am stopping this session here. Let us see next time. Thank you.